This is the second part of the 25th lesson in heat transfer. In the second part of lesson 25, we will develop a list of applications in which thermal radiation heat transfer is important. Thermal radiation heat transfer is often important when temperatures are high or when rates of convection heat transfer are relatively slow at lower temperatures. By the end of this lesson, you should be able to provide an example of a technology in which radiation heat transfer is important. On with the lesson.
So I want you to spend some time thinking about applications that you can think of where radiation heat transfer would be important. And as just a rough guide, I would say anytime you have high temperatures, where high is, say, greater than 500 C, usually radiation is the dominant mode of heat transfer, meaning you could probably neglect the convection and you'd get the problem pretty close to right. That's not to say that it's not important at low temperature problems. It can be, especially where problems have free convection, but it's not the dominant mode of heat transfer at the low temperature, right? Whereas it usually is at the high temperature. All right, so I'll give you a minute and a half to come up with as many applications as possible where you think radiation is important. Go for quantity over quality.
Now, what I would like you to do is pause the video and write down an answer to the question.
Let me hear some of the things on your list. So first, someone on Zoom, you got to put it in the chat or just unmute yourself. An application from your list.
I'm sorry, microwaves.
Okay. Microwaves. I'm going to put microwaves over to the side and we'll talk about it in a bit. So something else, someone in the room, Rachel and Abby.
But we were talking about how, like, with plants, they make their food from
Photosynthesis. Okay, so yeah, where does photosynthesis fit into this? I'm going to put that over to the side too. Also, really good idea. Both of those are really good thinking because they both definitely have radiation in them. We'll think a little bit more in a bit whether or not we want to categorize it as thermal radiation or not. Okay. Other things from the list. So Aaron and Brennan.
I had greenhouse.
Greenhouses. Okay. From the middle, Cade.
You said concentrated, so.
Thank you. Concentrated solar energy. Okay. Haley, Noah, Jared over that corner.
With radiation, what you get for cancer.
Okay. Okay, so again, I'm going to put, I'll say radiation therapy and what is the nature of that and what's going on with that. I'm going to put that over there, but good. It's good that you're thinking of that. Well, again, we'll have to think about, do we want to categorize this as thermal radiation or not? Okay. But it's a good thing on the list. Other things, maybe up in the front, Nate, Chris, Connor.
We had any sort of like manufacturing process that was all molten metal.
Okay, molten metal processing. Okay, forging. Good. yeah, those are some good things on the list. So you're in the ballpark, and you're thinking radiation for sure. So let's think a little bit about the microwave. So the microwave definitely increases the thermal energy content of the food that we put in it. Do you notice that some food does better than other food at heating? Have you ever thought about why that is? Noah?
Is it something to do on like water?
Absolutely, 100% is related to the water content of food. So water is a natural dipole, right? So the oxygens and the hydrogens exist on a little bend right that's not a straight molecule like carbon dioxide is, because of the polarity in order to charge balance. And because of that, when water can rotate back and forth, and it's called a dipole oscillator. And lo and behold, the nature of the microwaves, when you have a microwave source, when you have a source of radiation, microwave radiation, the way that you create the microwave radiation is you excite a dipole moment, right? We do it artificially by applying a potential to make the dipole oscillate and make microwaves come off, which is why water, which is a dipole, does so well at absorbing that microwave radiation. Now, I would say that the net effect is the heating, but I wouldn't call the microwave radiation thermal radiation, because the nature of the emission is artificial, right? We're actually applying a potential and making a thing emit microwaves when it wouldn't naturally, just from its own temperature, emit that radiation at that level. But when you get to the food heating part, I would say that we have a thermal generation process, right? We have an absorption of those microwaves and a conversion of that microwave energy into thermal energy in our food via the heating of the water molecules. So would it fall under heat transfer? Yes. Is the microwave emission itself thermal radiation? I would say no, right? Because we actually have to do something special to make that radiation come out. Does that make sense? So I would say that microwaves are not thermal radiation, but definitely radiation. Okay. Photosynthesis, really good. So this, I would say, yeah, depends on how we want to view it. So the nature of the reaction of photosynthesis is, so it's an endothermic reaction, right? And it requires energy. That's why it's energy, we end up storing, like the plant stores up energy, right? Like it takes the energy in and stores it. So it's endothermic. And it's using sunlight. So sunlight is 100% thermal, okay? So the nature of the radiation from the sun is related to the wackiness of the molecules of matter in the sun sphere, and they're bouncing around, and the electron transitions and all of that stuff is all what gives nature to the radiation. So I would say that fits. So I would say photosynthesis would be it's like an acceptor of thermal radiation, and it uses that thermal radiation and converts some of it into stored up possible work, but not all of it, right? We know not all of it because the leaf looks green. And the reason the leaf looks green is because it reflects the green part of the sunlight into our eyes. So this, I would say, would fit as an application. So for sure, yeah, I'm gonna say this is okay, thinking about it. That's the first time anyone has ever said photosynthesis in this class. I've been teaching it for 6 years. That's really nice. Radiation therapy. So I'm not an expert in this, but I think from the little bit that I do understand, they should kind of fall into the microwave category. The nature of the radiation and radiation therapy is a little different than thermal radiation, because I'm pretty sure that the idea is that you use this short wavelength radiation, because the short wavelength radiation is the one that is highly disruptive to our cells, right? That's why in nuclear disasters, when you have nuclear decay, it's so dangerous, because the gamma rays like break our cells up, like they destroy everything, like the very nature of how the molecules are lined up, right? So I think that's the idea in radiation therapy, but I'm not an expert, because we actually want to break the cancer cells up, right? Like destroy them. via this radiation. That would not happen with visible light or maybe a little bit with UV, but I think it's a little different. Does that make sense? Yeah, but it's good that you're thinking that because it's still radiation. But again, it's the nature of the emission. I think that's key in distinguishing between thermal radiation and other forms of radiation.
What would nuclear bombs fall under that?
Nuclear bombs?
That'd be a thermal.
I would say that I would say it's more a nuclear reaction than it is radiation. So there is probably radiation emitted in the blowing up process, but you actually have a nuclear reaction. You have changes of, I don't remember what the bombs were, but right, from like hydrogen to helium, for example, right? So it's like a nuclear conversion more than it is radiation. Does that answer your question? Kate?
How does a fire, like a bonfire, is that considered?
Ooh, definitely. Fires definitely fall into radiation. Okay, and so both because of the temperature associated with the combustion, like when you look at the net heat transfer, there's an exothermic release of energy in the oxygen. When you burn something, right, it's taking up oxygen, and there's an exothermic energy release from that. And usually it's so intense that the heat transfer isn't sufficient to keep it cool, which is why it gets hot. And then the temperature of the coal itself radiates energy. And then you'll also see that there are gas molecules around the combustion site that also can emit radiation. And that is, even though the reaction is not radiation, the temperatures that the molecules come to causes there to be thermal radiation. There's emission because of the temperature of the molecules. So yeah, it would fit. Fire fits 100%. And fire, I would say more generally, in my list, fits with combustion processes. So when you look at flames, right, and you burn even gases, right, the flame temperatures are related to the temperature at which the gas molecules in the combustion flame reach, which is partially related to how much energy is released in the combustion process and the heat transfer that's going on to get the energy out. And so you have hot flames and cold flames, and you can affect the flame temperature by the air to fuel mixture ratio and all of that. It's really, really interesting stuff beyond what we're going to cover in this class. So if you like that type of a thing, you could take an advanced radiation class in graduate school or from ASME, for example, and look at what's called volumetric radiation, which would be covered under this. Okay, you actually have radiation from gases. We're not going to deal with radiation from gases. We're going to pretend that the gases don't interact with radiation at all, right? And the radiation goes from surfaces to surfaces. But it's an example for sure. Solar energy fits, heat transfer in space, big time radiation. There's no air to reject energy to. So if you have, for example, your satellites that have some energy conversion process, because I don't know, they have electronics, right, that dissipate energy, and you don't want the satellite to just burn itself up, you have to get that thermal energy out. You only have one option. You have radiation as the option. That's it. And so radiators are really, really important for space applications. 100%, really important. Yeah, and there's all kinds of other applications. Your list is really, really good. You are right there on it in terms of thinking this through. Other questions? Because I think it's good to have these things in our head before we launch into the nitty-gritty.